So the new number 5, I should say, because there was no number 5 before. So these are the ones that we covered. I created a number 4 and a number 5, and I said we would start with the number 5 today. All right. So we start off with x-intercepts. Right. When it comes to sketching, we're looking for intercepts, any kind of symmetry, behavior, and then we create a sketch. It's not going to be perfect, but it doesn't have to be. All right. So the one thing you don't want to do, just thinking forward to a test, is you don't want to just go into a calculator, grab a table of values and just plot them. That's not going to get you any credit. All right. So the x-intercept approach is to replace replace the f of x with 0. So f of x equals 0 and solve for x. All right. So in my original function where I have f of x, I'm going to make that a 0 and I'm going to solve the remainder of the equation. It's already in factored form, so it shouldn't be that bad. One thing that people tend to lose sight of is the x. You know, they kind of treat it like a coefficient, which is dangerous. Speaking of dangerous, I don't know what to do with my phone. It's in my pocket. All right, that's good. Just got to make sure I have that available in case anybody messages me, lateness, etc. So set each of my factors equal to 0. We talked about the little shortcut, which is to say whatever the factor is inside, or whatever the binomial is inside one of the factors, you could take that and just reverse the sign and you have the roots. All right. So that's an approach, a strategy that you could use. All right. Or you could just do what I'm doing here and solve each one of them. So the first one's already solved. The second one, I would take the square root of both sides and get x minus 1 equals 0. X plus 1 equals 0 would be the third one if I just take the cube root of both sides of the equation. So just bringing it in, that would be square root here to offset the power of 2, but do it to both sides to keep the equation balanced. Then cube root here, again, applying to both sides. All right, so then we set each of those factors. We already set the factors equal to 0. We solve for the value of x in each case. So x equals 0, and x equals 1, and finally x equals -1. All right. So then we grab the y-intercept and do it over here. So I keep it on the same screen. That's where you find the result of f of 0. So that means replace every x with a 0 and solve for f of x. But I'll keep it simple. I'll just say solve for y. All right. So our original function, again, this, I'm going to replace each x with a 0 and solve for this. And again, since we know that y is a function of x, y equals f of x. So I would say y is equal to 0 times 0 minus 1 squared times 0 plus 1 cubed. All right. And so in doing that, we get a result of 0. The y-intercept equals 0. This is really more about the process. I mentioned last time that if you have an x-intercept of 0, you must also have a y-intercept of 0. So we could have just assumed that, but it's always a good idea to get the skill down, because actually I think this is one of the first times that that's actually happened, at least for the problems that I made up. All right. So then we look at symmetry. All right, so symmetry.
Sorry, Professor. It's Chris Adeye. I'm here. I had an emergency call.
Okay, thank you.
Thank you. Yeah, sorry about that.
Okay. Just going to put that in real quick before I forget, because I will. Okay. All right. So then for symmetry, I'm going to, well, I mentioned last time, and it really is true. You could do it one of two ways. You could simplify by finding f of negative x, or you could use some test values. All right. I find that most people prefer the test value approach just because it's a little bit quicker, and you don't always have to generalize for the entire function in order to get a sense of whether or not there's symmetry. Right. So let's say I do find f of 1 and find f of -1. The relationship between these two values, whatever you choose as your first test value, negate that for your second test value. Whatever the relationship is, they're either going to be equal numbers or exact opposites, or there's no symmetry. All right. So I put in a 1 for my function. If you look closely, you see that we have a 1 minus 1 here, which gives me a 0. So that means that this is going to 0 out, right? If I put in a -1, we run into the same issue where it zeroes out. Now, that in and of itself isn't bad. The problem is the values I chose for my symmetry test happen to be the roots of the function, right? So just because the roots are symmetrical doesn't mean the entire function will be symmetrical, all right? What I'm looking for is a counterexample. And what I mentioned last time is you could choose a couple of values. If it works out that the numbers, the final values are the same, then you got to do it again, right? At least 2 attempts. If they're different, then you can stop because you found the counterexample. So I'll try 2 and -2. 2 times 2 minus 1 squared times 2 plus 1 cubed. And then -2 times -2 minus 1 squared times -2 plus 1 cubed. Right. So this is, a little bit beefier in terms of the computation, but it's still not terrible. All right. In the first computation, we have a 2 minus 1 that's going to give me a 1. Squared is 1. So 2 times 1 is going to give me a 2. Then I have 2 plus 1 is 3 cubed. 3 cubed is 27 times 2 is 54. So I just want to see if this computation is going to lead to the same thing or the exact opposite or some other number. All right. So here I have -3 squared is going to give me a 9. -2 plus 1 is -2. Cubed is, -2 plus 1 is -1. Cubed is -1. So I have -2 times 9 times -1. That's not going to give me a 54. It's not going to give me a -54. It's going to give me a positive 18. So there is no symmetry. Specifically with the axis or the origin. All right. So we can't rely on that like we did the previous problem here to get a sense of the shape. So we're kind of limited in what we can do. Right. But we do know multiplicity. The x equals 1 has a multiplicity of 2. All right. So we get a highlighter involved. That power of 2 corresponds with the multiplicity. The x equals -1 has a multiplicity, mult of 3, same deal. But you also have the x equals 0. That didn't have a power other than 1 associated with it. So this one is going to be multiplicity 1. So we have a graph that's going to behave like a line around x equals 0, behave like a parabola around x equals 1 and behave like a cubic around x equals -1, right? But then we also want to take into account the behavior of the graph, the function itself, right? So for that, we look at the leading coefficient of the function, I'm sorry, the leading term of the function, and see what kind of model that should behave as, all right? And generally, if you could pull the leading coefficient, that's even better, along with the highest power, because then you know not only the shape, but the direction, right? We've been doing that, but it's sometimes easier said than done, right? So if I were to distribute this out, which I'm not going to do, but in distributing this out, I would get f of x is equal to, we'd have an x to the second power, an x to the third power, and an x to the first power. So that's x raised to a power of 6, all right? There would be other stuff after that, but I only care about the first term. So that x to the 6th power, that's a degree 6 polynomial. It's going to look like, oh, why does that not show up on my screen? It's going to look like one of these two things. All right. So it's going to either start low or end low, or start low and end low, or start high and end high. And it's going to have some wiggle to it. All right. These were the examples of negative leading coefficients. These were the examples of positive leading coefficients. I made a note of that below, but people don't always really love the inequality notation. So my leading coefficient here is positive. So I now can say that this is going to start high, end high, and, a bunch of wigglies along the way. It's going to look something like that. All right. That's just a rough sketch of the parent function, x to the 6th power. All right. But what I want to do is use what I now know about this graph and do the sketch. And again, you see how I'm tucking the graph into like this little tiny corner here? Yeah, I can zoom in, but I'm trying to get across the idea that it doesn't have to be this big elaborate graph on graph paper. In fact, it shouldn't be on graph paper. It should, when I say sketch, I mean a sketch. Get that stuff in there so we have a little frame of reference. The y-intercept is 0, all right? So I don't have to worry about scaling too much. I'm going out as far as -1 and +1 in the horizontal axis, all right? So I'm just going to go, here's -1, here's +1. I know I have 3 roots, 3 distinct roots, I should say. It's going to start high and end high. So I'll put a boop and a boop. All right. Around 0, it's supposed to behave like a line, but around the -1, it's supposed to behave like a cubic. All right. So it's got to look something like this. So somewhat cubic, but then it has to turn around and grab the origin as if it were a straight line, right? It also has to behave like a parabola around x equals 1. So it must turn around again, behave like a parabola, and then shoot on up to, well, I just arbitrarily put the arrow there, but shoot on up to the arrow, all right? So we have behavior as if it's a cubic. And admittedly, that's not my best work. I probably went a little too low with it, but again, it's a sketch, so it doesn't have to be perfect. So, something like that probably. But it should have this little wiggle here going on. So in, leveling off, and then down. All right. So like this. So I kind of got it. But then around here, it's very linear. And then around here, it's very parabolic. All right. And so that is an effective sketch. Now, again, I told you last time, and I'll reinforce this as we go. Yeah, there's turning points here, and I could be way off of where those turning points are, but that's not part of this this process yet. All right, we got to learn some skills associated with turning points before you could even hope to do that. All right, and you could check it with the calculator. I'll just bring up NumWorks. Apologies for the jarring screen movement here. But if I go into my graph or, no, it's a different problem. I was like, am I that lucky that I actually have the right one in? But no, I could just kind of modify this one. So an X in front, then an X minus 1 squared, then an X plus 1 cubed. All right, so put that in, double check that you put it in right. Graph, kinda. It's in the same neighborhood. It's in the same vein, so it should feel pretty good about that sketch. I can tell you that when we take a test on this, there will be one problem, exactly one problem that's just like this. Structured the same way, asks you to do the same stuff, x-intercepts, y-intercepts, symmetry, address all that stuff, and come up with a sketch. Right. So you would be, and I really mean this, throwing away a lot of points if you just created the graph by, doing one of these moves. Go to the table, just grab some points, plot these points, and see what happens. It's not going to work out. All right. You won't get the credit. And it's not me being a stickler, like, oh, you must do it my way. This is a skill that you want to have down before you step into a calculus class. Right? It makes a lot easier when it comes to finding relative extrema, some high points and low points of a turning point, and other things. I'm not going to get into all the different calculus terms that might come from this, but there's a bunch. There's a whole unit on it, right? And so you're at a disadvantage if you don't develop comfort making sketches of graphs rather than point by point, get it from the calculator, plot those points, and go that route. And I know people will get upset and get their test back and be like, oh, I don't understand why I lost so much credit just because I didn't do it your way. Why should I lose that credit? And it's like, well, this is the way. This is the way. So that's polynomial functions. I mean, it's not all there is to it, but that's all we're going to focus on for now. So we move on to rational functions. All right. So the question was, if the roots are not symmetrical, can we assume there is no symmetry? I would say generally, but sometimes there's complex roots. So that kind of throws a monkey wrench into the whole thing. But if there are real roots, and they are not themselves symmetrical, then you could expect that the whole polynomial will not be symmetrical. Good question. So rational functions, we call it R of X instead of P of X, right? R of X are R for rational. The P of X that makes up the numerator of the rational function is some polynomial. So it's the same kind of P of X that we've been working with. I just kind of flip-flopped and called it F of X, so a little inconsistent there, but generally try to stick to P of X for polynomials and R of X for rationals. But the issue you run into, unless you want to get subscripts involved, is if you name one function P of X, the next function should be something other than P of X. So the bottom is also a polynomial function, but it's different from the top. So these are both, each of them, polynomial functions. All right. But just to kind of cross the T's and dot the I's, even though the bottom should be a polynomial function, I do make the statement that it can't be equal to 0 just because you can't have 0 in the bottom of the fraction and still be defined. All right. Vertical asymptotes, vertical line that a curve approaches but never touches. So I'll just give a quick example here. Just going back to good old numworks. I'll show you how to find them in a minute, but I want to show you what it looks like first. So I don't need this template anymore. I'm going to go 5 minus x. I like to put the division symbol in first so that I don't have to worry about parentheses. 5 minus x, x squared minus 4. All right. So lock that in, go to the graph. And you have, this is what the graph looks like. I'm just going to sneak this in here real quick. The things we do to get out of having to actually hand draw a graph. That being said, we're going to have to hand draw graphs for this too. Copy, done, save to photos. I do that. I tend to save it and then knowing that I'm going to end up probably deleting it later on down the line. So this graph, well, this is the graph of R. Oh, my pen's not on. Sorry, R of X over here. So what's happening is this graph extends to negative infinity. As it goes to the left, it'll keep getting closer and closer to that horizontal axis until it gets to negative infinity. Going on the other side, it'll eventually get to, I don't know why I put the negative symbol there. It's one of those days. It'll get to positive infinity, right? So it'll keep increasing, getting ever closer to the horizontal axis. If it ever got to infinity, which it can't, but if it ever did, then it would actually make contact with the line. But that's all theoretical, right? Now we do have a point, any point living along this line. What happens is, oops, trying to get my point going here. You have a point that's over here at negative infinity, traveling along the curve, along the curve. It's going to increase forever, approaching a vertical line. Right. And this is where we run into issues because we tend to think of things in terms of the passage of time. So if this is increasing infinitely, then how do we ever get to a different part of the graph? I lost my point. So what's happening is this part of the curve over here is approaching a vertical line. All right. Which I'm going to make dashed. Most calculators aren't going to show you that, but there is some boundary that this part of the graph is approaching. So what we have to assume is that it's going to increase without bound as it gets closer and closer to, that looks like the line is at -2. As it gets closer and closer to the x value of -2, it's going to increase infinitely. So now we have to use our imagination, all right? So it gets as close as it can to -2, the x value of -2, knowing that it can't get there. It hops over the line down over here and starts working along this part of the graph until it approaches another vertical line that it can't seem to get around. All right. So that would be this line over here. So same deal. It's going to travel along this curve, getting closer and closer to the x value of 2. Because again, this is a scaled graph. So this is at -2. This is at +2. All right. In fact, those are the equations of the vertical lines would be x equals -2, x equals +2. All right. And then assuming that it could eventually get to negative infinity over here, it's going to hop the line and come back along this path and eventually go out to on its merry way to positive infinity, right? Those two vertical lines that it approaches but will never touch, those are called vertical asymptotes. So VA, VA, VA for vertical asymptote. So sometimes you can pick it right off the graph. It's really nice. Sometimes you can't, all right? So the way we handle it algebraically is by looking for any instance in which the function would be undefined, right? So we ask ourselves, where is R of X undefined? Because those would be the points where the graph doesn't exist. And up here where I was saying Q of X can't be equal to 0, I mean, one way to interpret that would be to say, I don't want an equation of R of X equals P of X over 0. This would be bad, right? This would be undefined. But when there's a variable in the bottom of a fraction, it's possible that the function could be defined most of the time, and there's only a couple instances where it's undefined. And that's how it manifests itself in the graph. There's a break in the graph, right? So to find where a function or an equation or whatever is undefined, you just take the bottom of the fraction and figure out under what circumstances that could be equal to 0. Sometimes it's just a matter of looking at it. Sometimes you solve an equation. So I'll do it using the algebraic solution. X squared minus 4 equals 0. For a quadratic that's in binomial form, you can go after it a couple of ways. You can factor it if you want, but I think a nicer way to handle it would be to solve for x squared and then take the square root of both sides. The one drawback to this approach is when you take the square root of a number, you have to account for the fact that it could be positive or negative. So we get x equals plus or minus 2. That goes back to completing the square, which would give us x equals 2, x equals negative 2. All right. So R of X is undefined. When x equals 2 or x equals negative 2. Those would be the vertical asymptotes. All right. So that you have a couple of different ways you can handle it. One would be the graphical approach. If it works, great. But I mean, I really just kind of supposed that that was 2 and negative 2. It might not have been. It might have been like 1.725. So I have vertical asymptote here of x equals 2, x equals negative 2. And it's now confirmed because I looked at the graph. I suspected that it was 2 or negative 2. And as it turned out, I was able to verify that analytically. All right. So if you have a vertical asymptote, odds are you might have a horizontal asymptote. So how do we find horizontal asymptotes? Well, the answer to that is actually a whole lot easier, right? The explanation for where these rules come from is straight out of the limits concept in calculus. So we're not there. So we're just going to rely on rules at this point. For a horizontal asymptote, you can actually, for certain parts of the graph, physically make contact with the asymptote itself. In the case of a vertical asymptote, these two could never merge without getting to infinity, because if they did, it must mean, since the vertical line is rigid, that's not changing its shape, but the shape of the curve is changing. Here it's pretty shallow. Then it starts getting steeper, 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 steeper still. If it could get to infinity, it would go perfectly vertical. All right. If it goes perfectly vertical, just going back to one of the first things you learned about lines, the slope of a vertical line is undefined. All right, so it would no longer be a defined function. So we'd have to assume that in the land of functions, that there's no way that this could ever make contact with that vertical line, because if it did, it would no longer be a defined function. Whereas if you continue going out forever over here towards infinity, even if you made contact with it eventually, well, a horizontal line is still a function. So that would be okay. All right. But also, who's to say that you don't have a function where it's like, I'll show you real quick, a horizontal asymptote. So it approaches the line for the extremes on the left, but then it comes back in and it makes contact with the asymptote itself, and then it continues on. Horizontal asymptotes are more of a behavioral thing in terms of how it behaves for extreme values. So you could have, and I should probably put this down below with the horizontal asymptotes. Here's an example. You could also have what we did above, or even a simpler one where maybe there's only one vertical asymptote. Maybe it looks something like this. All right, so this would be my horizontal asymptote. I'll do it in blue here. So here's an HA, that blue line. This would also be a horizontal asymptote. But you see in one case, the graph actually intersects the horizontal asymptote. In the other case, it doesn't. All right. The good thing is, it doesn't matter what happens in the short term. Asymptotes are only relevant for the long term. So as it gets closer to infinity or negative infinity, then it should adhere to the rules of being an asymptote. Right. And that applies for both graphs. Right. The way we figure out where the horizontal asymptote is, because it might not be necessarily on the y-axis or the y-axis for vertical, x-axis for horizontal. It could be somewhere else. So we use these rules to help us make that determination. All right. The first rule, I call them the M and N rules. I'm not the only one who calls them that, but we just use M and N to represent the highest power on the top of the fraction and the highest power on the bottom of the fraction. How they relate to one another is going to dictate whether there is a horizontal asymptote. All right. Dictate. Dictate is the first word of the day. Dictate. Like I am going to dictate the notes to you today. I even gave you the sentence. All right. So, for example, if the power on the top is more than the power on the bottom, then there is none. Meaning there is no horizontal asymptote. There's no horizontal line that the graph will approach for extreme values of x. The other simple case, relatively anyway, is if the high power on the top is less than the high power on the bottom. I'll show you the examples in a minute. That would give us a horizontal asymptote specifically of y equals 0. That's the x-axis. All right. If the powers are the same, then it's going to be some other horizontal line. That some other horizontal line comes from taking the coefficients of the terms with the highest power and dividing them, creating a ratio out of them. All right. So if you have your function written in descending order, it should be easy enough to pick this information out. All right, so let me show you an example. Well, I'm going to show you two examples, but I'm going to do the second one first. All right, because that's a little bit clearer. So the first thing I would do in this example is rewrite it or just think of it in descending order. Highest power first, and the next highest, and the next highest, and so on. The bottom's fine. You have a power of 2, all right, followed by a power of 1, assumed power of 1. And then you have a power of 0 for the 1. You might say, well, it's a power of 1, but it's not, because we got to think about what the power would be of the variable attached to a 1. Next to any whole number, well, actually any value, but specifically when dealing with polynomials, they would be integer values. If there's any standalone integer value, there's always an assumed x to the 0th attached to it. So this is assumed. All right. Now, on the top, they have it in ascending order, lowest power to highest power. So I would rewrite that as negative x. I'm going to write it as negative x to the first plus 2. Now, again, you got a naked number here. There's an associated sign that's assumed to be a positive. So that's positive 2 that goes off the end. Now, also, we know a coefficient, if it's just a negative sign, that's just a hidden -1. So I'm just going to tuck that in there also. All right. And then while I'm at it, on the bottom, I have an understood coefficient here of 1. Right. It's going to be these two terms that I care about in determining whether there's a horizontal asymptote. My ellipse game is off today. There we go. All right. So the top number, or the top exponent, I should say, associated with the leading term, is going to be 1. The bottom one is going to be a 2. The top one is the m. Oops. M is equal to 1. N is equal to 2. Try to keep consistent with my color scheme here. The relationship here is that m is less than n. So that means the horizontal asymptote has to be y equals 0. Right? So those coefficients didn't matter for anything. They would only matter if these two powers, the green and the blue, if they were the same. Right? They're not the same, so it's irrelevant, or horizontal asymptote is y equals 0. Right? I can pop this into the calculator and take a look. Just a little verification. We'll use this template, make some modifications. On the bottom, we have x squared plus 2x plus 1. Now, again, there might be, well, again, I didn't say this the first time. If there is a horizontal asymptote, there still could be vertical asymptotes, right? It's just they didn't ask us for that. They didn't really ask us for anything, but we're just focusing on horizontal asymptotes right now. All right, so graph, if you look closely, I'll bring it in. Done. Oh, I want to copy it first. Copy, save the photo, save for posterity, and paste. All right, at least so I can mark it up. I got this extra business over here. Hold on one sec. Edit, crop. I don't want that. All right. So as you go out towards negative infinity over here, or positive infinity over here, it does appear to be closing in on a line. Now it's kind of tricky. Over in this neck of the woods, on the right-hand side, it looks like it's already made contact with the x-axis. But that's actually because I'll draw like a more dramatic version of it. What's happening is that this is approaching some vertical asymptote over here. Then it's coming back down, grabbing some y-intercept, passing through the x-axis and then coming back up on the underside. And it's approaching it in that regard, right? So it's getting closer and closer to the x-axis, just not in the way that we would expect. And this graph, it kind of merges a little bit, so it's hard to tell. So if you adjust your axes, I'll turn it off auto and make my maximum X like 40. Really doesn't matter. Just want to show the dramatic relationship here. And all right. I'm also going to bring it in closer to the x-axis. So you see how on the vertical axis it's going up to like 60 now. I don't want that. So I can change my vertical axis so that it goes from, like, let's say -1, turn it off auto, -1 to 1. I want it to be really close around the x-axis. All right. So it's going to go out far in the y, but stay really close in the x. What did I just do? I just reset. No, I didn't. It's good. I just didn't confirm it. It's a little bit nicer this way, right? You can see now that it actually crosses the x-axis and then comes up from the underside, right? But it does justify the horizontal asymptote being y equals 0. But we want to be able to get it like a sight recognition kind of deal, right? You look at the function and say, well, clearly this has a horizontal asymptote. I promise that'll help you when it comes to finding limits in early part of Calc 1, right? Infinite limits, the first thing that the teacher is going to say is, remember those horizontal asymptote rules? And you'll be like, dang it, no, I don't. And then that'll be the end of it. Now you'll have to memorize them, but it's better to start working on it now because it's always easier to retain something the second time around. So going back to number 1, I want to rewrite. So R of X, I'm thinking of the one on the top as 1x to the 0th. And on the bottom, 1x to the 1st. Much simpler, but people struggle with the loose coefficients there because it is like, well, where's the power? There's going to be a mistake. That's probably where it's going to happen. So my m value and my n values are 0 and 1. So the relationship is still the same. The m value is less than the n. So therefore, we have a horizontal asymptote at y equals 0. All right, so this graph will also approach 0 for extreme values of x. All right, this one's a lot easier to put in. I'll just wipe it out, actually. I'll steal this one and I'll just tuck in a 1 divided by in front. Oh, that's not a 1. All right, then look at the graph. And it maintained the same window that I had before. So for this one, I might want to go to auto and let it reset itself. All right, so as you go out to the left, to the right, it does appear to be approaching the x-axis, which is the line y equals 0. Now I wanted to kind of sneak in. Oh, you know what? I was going to say I wanted to sneak in another example, but I don't need to because shockingly, I remembered to create one that had a different kind of horizontal asymptote. All right. So looking at number 3 on the next page, talk about n behavior models for rational functions. The n behavior model, which we call EBM, rational function and the n behavior model behave the same way as they each move out to negative infinity or positive infinity along the x-axis, right? So you divide the leading term of the numerator polynomial by the leading term of the denominator polynomial, and that's the function that it's going to behave like, right? So I'm going to use this example, and we're going to sketch the entire graph, but I also want to get an idea of the behavior of it, right? So it's already in proper descending order. So that's good. If I want to determine my horizontal asymptote, sorry, the horizontal asymptote, I would take the highest power on the top and the highest power on the bottom and see how they relate to one another. So the m value is 2, the n value is equal to 2. And so the m value is equal to the n value. So therefore, the horizontal asymptote is the line y equals, scary formula, a sub m over a sub n. All right. On the previous page, I mentioned that those were the coefficients associated with the leading term on the top and bottom. So we have the understood 1 here. That 1, so the 2 is the m, that 1 is the a sub m. Right? We use a to or letters early in the alphabet to represent coefficients or constants. So I'm saying that this is the mth a value, which just means it's the a value associated with the power that we're calling m. With the same idea on the bottom, this is my n, so that makes this my a sub n. So my horizontal asymptote is y equals 1/2. All right. So that's going to be my end behavior model. But the thing is, this concept works for more than just horizontal asymptotes. It just turns out that this one has a horizontal asymptote. All right. So what I could have done, if I followed the letter of this end behavior model method, I could have taken just the first 2 terms. So I'll rewrite the function f of x. I'm sorry, not first 2 terms, first term on the top and the first term on the bottom, and divide them. So if I take these 2, and divide the top by the bottom, we would get an end behavior model, EBM, of y equals x squared over 2x squared. Which would simplify down to y equals 1/2. The issue that we run into is related to the other functions, these ones over here. If you try that same technique, you end up with a rational function as the end behavior model, so it doesn't really help. And it's kind of like defining a term using the term in its own definition. All right. I never can think of an example off the top of my head, but yeah, it's like likelihood. No, I got to think about it, but my brain is not where it needs to be right now. Yeah, I wanted the first one that popped into my mind is like shoeless. It's like, what's the definition? Not having shoes, but I think that's a reasonable definition, you know. But although the shoe and the shoeless, you know, oh, shoelessness. I say something is shoelessness. Like the word is shoelessness, like the absence of shoes should be the definition. But let's say I define it as the act of being shoeless. Shoelessness, act of being shoeless. It's like, okay, well, what the heck does shoeless mean? Right? It's not the best example, but unfortunately, it's the first one that came to mind, and I tried to make it work. All right. So the directions here use the end behavior model as well as your knowledge of rational functions, which is literally the worst thing that a student wants to hear, because that requires you to know stuff. You know, it's not procedural like with the polynomial functions where I said find the x-intercepts, find the y-intercepts. You know, I could say it like this: use your knowledge of polynomial functions to graph, but I'm a little bit more explicit with that. Here, I just say your knowledge of rational functions because the only possibilities are asymptotes, along with any possible roots that might exist. All right. So we just discovered whether it was, and these two, they accounted for the same thing. So this end behavior model approach or the horizontal asymptote approach, they both gave us the same information. So this is a either or kind of deal. All right. Oh, it's not a line. I don't think this matters for anyone, but I realized that my iPad shows a time that's completely different than the actual time. So, and don't get me wrong, I didn't think it was the morning. I was just looking at the minutes and I'm like, wow, we're moving along. I got a lot accomplished in 41 minutes. Yeah, I didn't realize we were an hour in. So not as much as I thought. So vertical asymptote, we would get that by setting the bottom of the fraction equal to 0. All right. So if there are any common factors between the top and bottom, though, we need to account for that. All right. So I'm going to go back to my original function, f of x equals x squared minus 4 over 2x squared minus 8. All right. So I'm going to look at this and say, all right, is there any way I could simplify it? Because if you could simplify it, then, you know, it might not even be as complicated as we think it is. Right. On the bottom, we have a common factor. I wrote F, I meant to write R. That's what I called it here, right? Oh, no, I called it F, shockingly. Okay. So if I factor out the bottom, f of x is equal to x squared minus 4 over 2 times x squared minus 4. Now, if I'm just following the approach, ignoring any common factors, I might look at this and say, oh, okay, well, he said to take the bottom and set it equal to 0. Get a fresh new color here. Take that, set it equal to 0. Cancel out the 2, because if you divide both sides by 2, it goes away anyway. You get x squared minus 4 equals 0. Solve, you get x squared equals 4. Take the square root of both sides because it's a binomial quadratic. X equals plus or minus 2. And you might say, oh, well, this is like that other problem. We have a vertical asymptote at 2 and negative 2. But let me show you the graph. So I'm going to pop it in, x squared up top. Well, x squared minus 4, I should say. And then 2x squared minus 8 on the bottom. So I go into the graph. So I put the equation in, go into the graph, hit OK. And you're like, what's going on here? You know, it doesn't look like a rational function. It's supposed to have that look like a curve and an asymptote and stuff, like all the other pictures I showed you. This one just seems to be a horizontal line. What on earth is going on? You know, and you might zoom out, you know, so go to my my axes. And maybe I'll go out a lot further on in the x direction. I'll go out to like negative 50. Go to positive 50. I almost said in 50, like as if it were infinity. All right, let me go to the. I wanted to hit confirm, but I hit the wrong thing. Still looks like a horizontal line. That green line, that's not the x-axis. That's the function on top of, or appearing to be on top of the x-axis. So then you investigate further and say, well, maybe it's the y's. Let's bring that in. Maybe I'll go like negative 1 to 1 like it did before. Confirm that. It still appears to be a horizontal line. So then maybe you go into the table. You know, you get some points from the table and you see that there's a value that's undefined, but every other value appears to be the same. All right. But this only has whole number value. Maybe I want to get some negatives in there. So I set my interval, instead of going from 0 to 10, and make it go from -10 to 10. Confirm. A whole bunch of 1/2, something undefined at -2, undefined again at +2, and a whole bunch of 1/2. Then I look at the picture again and say, well, it's undefined at 2 and -2. That means there should be a vertical asymptote, but there is no vertical asymptote at -2 or 2. Otherwise, there'd be some curvature to it, right? So these are not, so they're not vertical asymptotes. These are holes in the graph. All right, they're holes in the graph. We call those point discontinuities. All right, and you know what? It's at this moment that I realized the perfect word that I was talking about before in terms of the words that define themselves. I'm sorry, they use the its own word in its definition. So a discontinuity is a point or a location on a graph that is discontinuous. All right, it's one of those terms that only really kind of works if you know what continuous means. Right, so a nice simple explanation is there's no gaps in the graph. It's a one full curve going from the left side of your screen to the right side of your screen, and no gaps along the way. The problem is visually it's hard to show a point discontinuity because it's so infinitesimal. It's easy to show vertical asymptotes. That's what we call an infinite discontinuity, but we'll just call it vertical asymptote. So how do we do this? Well, the way to handle it is to identify the location of the holes in the graph. We know we're plotting it at, I'll call this 1. We're plotting a horizontal line at 1/2. It's going to go on forever to the left and to the right. But at 2, I'm sorry, -2, it's going to be just a little gap in the graph. But it's hard to show a little gap, like where, if I draw it close enough and I zoom out, you might look at this and say, I don't see a hole there. It's like a stray mark on my screen. You go and try to fix it. So the way we handle it is by exaggerating it, by drawing an open circle. All right. Anywhere there's a hole in the graph, we exaggerate it by drawing an open circle. And that's the universal symbol for a hole in the graph. All right. So it's true that the end behavior of this is y equals 1/2. All right. That would be the line. And I mentioned before that you could actually make contact with a horizontal asymptote. Right. So what's happening is this function is always on what would be its horizontal asymptote, except for the points where it does not exist, which would be at -2 and 2. All right. So it turns out we have no vertical asymptotes. We have a graph that simplifies down to y equals 1/2. And you say, well, I don't remember simplifying this. It turned out that this was all we needed to do to simplify it by the nature of the function. It won't always be that way, but we kind of got lucky here. All right. The better way of doing it is to think about any time you see a rational function, can I simplify it straight away? The top has factors of x minus 2x plus 2. The bottom, we already did the part where we pulled out the 2. So that would also have factors of 2 times x minus 2x plus 2. And you'll see what would have been a vertical asymptote actually cancels away. So anytime you have, and you're left with the understood coefficient of 1 here. Anytime you have, I'll call them would-be vertical asymptotes, but the factors cancel away, there will be a hole in the graph somewhere, at least one. All right. It's tricky. It's tough getting used to, but when you do, it really pays off, especially in calculus. Another thing to keep in mind, like I said before, if you just rely on looking at the picture to come up with a sketch, you could miss out on the important details. All right. Worst case scenario, like create the graph, go into the table and see if there's any points where it's undefined. But the drawback on that is these were clean values. I'll show you. At -2, it was undefined. At +2, it was undefined. But what if the points where it's undefined were fractional? It wouldn't show up in this list. You could change the incrementing of the interval, but if you don't have a sense that there's a hole in the graph to begin with, you wouldn't know to necessarily make my step, like I'll call it 0.25. It'll go by 0.25, but what if it's 0.2? It's still not going to show up in the list. Right. So we want to be able to handle it algebraically, but we also want to be able to, make it as seamless as possible. So do enough algebraically to get the information that you need that's best suited to be done algebraically, and do everything else with a calculator. All right. Calculator being the second word of the day, calculator. Like, for example, we have a NumWorks calculator. Second word of the day, calculator, just the calculator part. Number 4. Not as nice as number 3, but perhaps it is factorable. We don't know. But I can get the end behavior just by addressing the two first terms, so top and bottom. So for my end behavior model, I would take y equals 2x squared and divide it by 1x squared, right? The understood coefficient of 1 here. Powers that are the same, so my end behavior model is going to give me the horizontal asymptote, right? If I simplify, I get just a simple y equals 2. All right. So it's going to behave like a horizontal line. Because it's a horizontal line, this is the horizontal asymptote. So you kind of cut out a little bit of the fluff. 20 some odd years later, I'm still paying off my student loans, and the place I went to is still calling on a daily basis to ask me for a donation. I will give them a donation as soon as I'm done paying off my loans. All right, we got a hand up.
Yes, sir. I heard that the second word was calculator, but I never heard you saying the first one.
Okay, so you probably missed the first one, and we generally don't announce the word of the day for other people.
Okay.
It's a private thing. So, folks, calculator is no longer the second word of the day. Be on the lookout for.
I'm so sorry.
Listen for another one. All right.
My apologies. I'm sorry.
No, it's all right. It's all right.
I'm not sure if it cut out or something, because I was writing the notes as you were going, and yeah. Well.
Oh, the first one was like 45 minutes ago.
Yeah. Okay.
All right. So yeah, I don't try to be difficult over stuff like that. It's just that it's a very dangerous precedent to set. Like if a person asks later on down the line, oh, I missed it, what was it? There's another person who's like, oh, I can just say that, even though I was at the gym for 45 minutes and not paying attention, so that's why I'm kind of a stickler when it comes to that. Not trying to be a jerk. I just got to make sure it's fair for everyone.
So is the calculator word still counting, or?
It will not count.
Okay, got it.
So there is a redemption opportunity. We're still waiting for the second word of the day. All right. So we have the horizontal asymptote. We could start plotting that, But just like the way we handled it for polynomial functions, we kind of want to wait on all the information that we can get before we start making the graph. Because if we do, and we find out that we should have scaled the graph, that's a pretty hefty price to pay. All right. So now we're going to look at vertical asymptotes, but I don't want to fall into what I did before. I'm going to see if I can factor this. The bottom definitely is factorable. The top, when we have a quadratic with a leading coefficient that's other than 1, or in this case, a polynomial, because it's not its own standalone equation. I prefer to use the trial and error approach, but I can tell you that the only way it's going to be relevant, the only way or the only reason I would care to factor the top is if it would help me cancel out one of the factors on the bottom. All right. So I'd look at this and say, is there any way using either a 2 or a -2 that I can end up with a product of 7? So that would be the question, right? Because the final terms should boil down that way. And if you're ever in doubt, take one of the factors. I'm just taking a guess here. All right. Let's say I choose to go with this factor. I'm going to put that in here and then just try to build this polynomial from that. All right. So this would, if this is x plus 2, then this has to be 2x. How am I getting from a 2 times this to a 7? It's not going to happen. So the middle term isn't even relevant. Without getting a fraction involved here, which I don't want, it's not gonna work, right? So you try it again, but with the other factor on the bottom. So you put an x minus 2, same deal. These two would have to multiply to 2x squared. And these two would have to multiply to 7. I'm not going to be able to figure out something on the top that would, even if it is factorable, again, very important, even if it is factorable, if it's not going to help me cancel a factor on the bottom, I don't care. All right. So that tells me I don't have to worry about the factors on the top. They're irrelevant. Okay. So I'm going to leave the top as is. I'm going to say f of x is equal to 2x squared plus 3x plus 7 over x minus 2 x plus 2. All right, so I'm going to look at the bottom now for the vertical asymptotes. My vertical asymptotes will come, because there are no common factors top and bottom, they're going to come from the solution of x minus 2 times x plus 2 equals 0. So set each of those factors equal to 0. And solve. And I have now my set of vertical asymptotes. All right. So I have my vertical asymptotes. I have my horizontal asymptote. Now I want to be able to come up with the actual shape of the graph. But at least I have stuff I can plot and I have a sense of scale. I know I can go by ones now. Now is the second word of the day. Like as in, I am going to make this graph now. All right. So at -2, x equals -2, I have a vertical asymptote. At x equals +2, I also have a vertical asymptote. I have my horizontal asymptote at y equals 2. All right. So I know boundaries. I just don't know where else I'm gonna, or where in this this set of boundaries I'm gonna make the curve. Now you can kind of like be reasonable about this. You can kind of sort of cheat, not cheat, you know, like I'm never encouraging that because that's just wrong. But like you get a sense of what the shape of the graph looks like by just putting it in your calculator. But at a minimum, we want to know if there are any x-intercepts or y-intercepts. All right. So I'm going to find x-intercept, y-intercept. One is always easier than the other. The y-intercept for an ordinary function, the y-intercept, if it exists, is always going to be the easier thing to do. All right. So I'm going to go back to my original function for the x-intercept. To find an x-intercept, remember, I'll make a little note here, little reminder, set f of x equal to 0 and solve. So I'm going to replace f of x with 0. And I'm going to solve. So it brings me back to what we were dealing with over here, whether the top is factorable or not. I disregarded it as being relevant for finding the vertical asymptote, but it might be really relevant when it comes to finding other things, like in this case, the x-intercept. So you can go after this a couple of ways. You know, it's pre-calculus. It's not technically an algebra course, so we don't want to get bogged down too much with that. We do have to have certain skills, but if you wanted to use the quadratic formula, for example, to figure out the roots here, or you could use a solver. I'll show you real quick on NumWorks. You'll see a function here called solver. Put in the equation, add the equation, choose a template if you like, or type it in from scratch. I'll use this template. So 2, 3, 7. And the whole thing is equal to 0. You can put the 0 on the left, 0 equals, or put it on the right like they have it here. It doesn't amount to anything different. Right. For a class that's pretty much, I'll say online, but remote instruction, there's so many ways that you could, without doing things the right way, figure out the solution to simple equations. So I'm never going to ask you solve 2x squared plus 3x plus 7 equals 0 because you just look that up. I discourage it, but there's not much I can do to stop you. All right. So that's why I show the solver technique, because it's really more about the work that you show in coming up with the graphs. That's what you're going to be rated on. All right. So if you do this and go to solve the equation, it gives you the solution. And you can see at the top there, the polynomial has no real roots. All right. So there is no real roots, or there are no real roots for this polynomial function, which means it never crosses the x-axis. But as I mentioned before, finding the y-intercept is super easy, barely an inconvenience. Replace each x with a 0. And this you can do, this is not, I don't say this out of hand or offhand. You could do this in your head. You're like, no, I can't. I'm not really that great at math. Yes, you can, because anywhere there is an x, you're going to make a substitution of 0. So any of the terms that have an x in it, they're going to zap away. They're going to disappear. And you're just going to be left with whatever the y-intercept is. In this case, 7 over -4. Or, you know, -7/4. So you put the negative wherever you want. All right. If you want to get a sense of what that is in a decimal form, I mean, you just go to ordinary calculator for that. So -7/4 we could so actually probably didn't need a calculator for that, but negative 1.75. So my y-intercept, here's -1, here's -2. I'm going by one, so I don't have to label that. I have a y-intercept here, roughly. This curve is never crossing the x-axis, so I don't have to worry about things like multiplicity. It has to approach these two vertical lines and go through this point. So if we assume that it's going to go down like this, there's really only a couple of ways that this could play out. One of which, and again, we're doing a sketch, so we have a little bit of freedom here. One of which would be something like this. Right? It's also possible, to be fair, that it could be something like this. Well, that last little bit was me just going silly. Could go something like this. As long as it doesn't touch the x-axis. All right. But the simplest path is the most logical one. Right. So we would make the assumption that it's going to play out that way. But again, you have freedom as long as you go through that point and don't touch the x-axis. All right. So that's that part of it. But then you say, well, what about all this stuff out here? So for this, we use test values. All right. So we use test values to find the other parts of the curve. Now, again, this is all prefaced by me saying, yeah, technically you just type it in the calculator and you'll see what the graph looks like. You just make it work. But getting the good understanding going into calculus, that's the key ingredient. All right. And by the way, I didn't put the little special note here. Find f of 0. That's how you do the y-intercept. Now for the other parts of the curve, use test values. Use does not start with the letter Y. Use test values. All right. So this is happening. This vertical asymptote is right here, a vertical line going through -2, and the other one is going through +2. All right. So what I want to do is I want to test a value that's less than -2. So test some value that's less than -2 and test another value greater than +2. Doesn't matter what it is, but obviously the simpler you keep it, the easier it's going to be. All right. So, because we already know what's happening in between -2 and 2. So all the nice numbers are already taken. 1 and -1 are irrelevant. And 0, we already did. That's the y-intercept. So the next best number could be anything, but I'm just going to go with the -3. So I'm going to find f of -3. And we do that by plugging into the original function. That's going to give me 2 times -3 squared plus 3 times -3 plus 7 all over -3 squared minus 4. And we're going to get a number. Might not be pretty, but it should help. It will help. All right. So on the top, we got 18 minus 9 is 9 plus 7 is 16. And then on the bottom, 9 minus 4 is equal to 5. All right. So that's like 3 1/5, so 3.2. All right. So a natural question would be like, okay, cool. What did that tell us? You know, so if I go out to -3 here, here's -3, and go up 3.2, and honestly, I have no idea where 3.2 would be, but this is where 3 would be, like right at the top here. So a smidge more than that is going to put a point on this curve right around here. All right. So what this is telling me is that I must be going through that point. And that's the only way that this could work. So I'm going to extend my vertical asymptote a little bit, just so I have a nice boundary to work off of. I want to approach this horizontal line and I want to approach that vertical line while going through this point. So it must look something like this. Now, if you happen to know that there's symmetry, then you could really streamline the process, but I don't want to make that assumption. It's harder to determine symmetry for rational functions than it is for others, just by the nature of the numbers, right? So we'll use another test point to see what's going on to the right. So over here, to the right of my second vertical asymptote, right? Oh, I guess I could have saved this. Get rid of it now. All right, so I need to now figure out f of positive 3. All right, so I'm going to do the same computation again, just with a positive 3. So f of 3 is equal to 2 times 3 squared plus 3 times 3 plus 7 over 3 squared minus 4. All right, so same procedure, plugging into the original function, but this time with a positive 3. And you don't have to go, like we tested for symmetry before with polynomials. You don't have to use opposite numbers. I could have used -3 on the low side and a 5 on the high side if I wanted to. It really doesn't matter. All right, but in this case, we got 18. 9 times 2 is 18, plus another 9 is 27. So we're up to 36. And then on the bottom, we have a 5. So that's 7 and 1/5, so 7.2. All right. What we want to be able to do, oh, sorry, this is like glitching on me. What we want to be able to do is just determine, am I living above or below this horizontal asymptote? And any number that's bigger than 2 is going to put you above it. Anything that's less than 2 is going to put you below it. All right. Now, 7.2 is really out there. So I'd have to keep going here. So this would be 4, 5, 6, 7, like up here somewhere. So my point is going to be living in, this neighborhood. If I had to just do a rough estimate. So I'll put this at 3. And now I really want to extend my lines. That's one of the drawbacks. I mentioned this before. We do all this, these, scaling of graphs or not scaling of graphs. It all depends on what the quality of the numbers are, right? If they're large, then we scale. If not, then we don't. But if we dive into the process and basically, this is an example of what not to do. I started making the graph before I saw what kind of numbers I was dealing with. Then you could kind of run into trouble. I see a hand up. Question?
Yes, I guess it doesn't matter when you do the computation, but I believe it's 34, not 36. I think you thought the 7 was a 9.
I sure did.
Yeah,
I absolutely did.
I
Thank
thought
you.
as much.
So 34 fifths. So that's going to be 6.8. Yeah, so you're right. It didn't really amount to much, but it could have. So cautionary tale. All right. So when I'm making my graph, I know that I need to go through this point while approaching this vertical and this horizontal. So we're living in this corner of the universe, I guess. And so this would be our rational function. And again, it's not a pretty process, but there's so many different calculus skills that work their way into this that it's definitely worth taking the time to do. Right. So, it also, if you really think about it, it does severely limit the number of questions I can ask you on a test. So you kind of, if you're looking for a glass half full kind of deal, that might be one of them. You know, one of the positives to take away from this. There's like 40 different steps in this, right? Same thing with polynomial functions. There's just so much going on. Like this has got to be half the test, right? So if you master these two concepts, you're already halfway there. So we only have a couple more concepts to dig into, and then we'll start reviewing for a test. But I mean, it's good and it's bad, because sometimes we want all right, just ask me 10 multiple choice questions and we'll be done with it. But that's not going to be helpful, right? Going through the process is what helps you get better at this, right? I've been teaching for around 25 years, been teaching pre-calc for most of that. And then also calculus, calc 1, 2, 3, linear, like everything that comes after this at the college, I've taught repeatedly. And so I know from whence I speak, like this stuff comes up over and over and over again. And the people who struggle in calculus, they struggle because they struggle with this stuff. All right. And they only struggle with this stuff because they didn't take the time to master the content, because it's really not, each little nugget is not in and of itself difficult. It's just remembering all the details that have to come into play, right? So you have the advantage of being in a remote environment, because my rules for remote instruction is all tests are open note tests, right? So you'll have examples in front of you, the ones that you take in class, the ones that you try on your own. You're going to be presented with a unique function on the test. You just have to follow the process, right? We do have one more concept to cover for rational functions, that's point discontinuity. So I'm not at this point going to give you a breakdown step by step of how to graph a rational function, except to say, do all the stuff that we just did. But there is an extra layer to it that we'll talk about next class. All right. So with that in mind, I'm going to stop the recording